So the question is how to assign probability. Consistent with the axioms, right? Of f, this f. So each of these sets we need to assign a p which is consistent with the right axioms of probability. The most popular way or the most important way is to start with a Riemann integrable function, which is a standard integration that we have been studying all along, right. So let some f be a non-negative integrable function on R, on the real line. It should be non-negative, right. What is the main other requirement, most important requirement that we require on f? We require this integral from minus infinity to infinity of f of x such that this is what? 1, exactly. So I have written it correctly, right? Please note, let f be a non-negative integrable function fn over on the real line such that its area as represented by the integral, the entire area is unity. Based on this function, how will we assign a probability to any interval? Okay, this has nothing to do again with remember, right, we are going back to the first part of this course where we only talked about omega f p, right. No, we are not really talking about random variables or anything at this point, we are just talking about the basic omega f p, right. Now we have nailed omega, let us say, as equal to r for the time being. It is not a big issue to shrink it down to any subset of r like 0, 1 or whatever, right. Then f we have said is going to be all of this. Of course, if you have omega as only some 0, 1 for example, then you won't even get anything of this kind. All of this will be inside the omega itself, 0, 1 whatever. So we don't have to worry about infinity when it's not there, right. Now p, if I don't necessarily need to always integrate from minus infinity to infinity, right. If I have a smaller portion of the real line, I can live with a function whose area is 1 only on that portion of the real line. I don't need to look at the entire real line, but the entire real line is useful in the sense once you solve it for this case, you have solved it for omega being any piece of that real line, isn't it? Okay. So what is p of AB? Okay, let us say the open it, well, there is a, right, we have to look at, right, okay, a distinction here. Do we take the open interval or do we take closed interval? It turns out it does not matter. All of these combinations will have the same probability. What 4 things can I do? As long as A and B are finite, I can look at 4 possibilities here, right? Is equal to what? Based on f, what should I do? I have to integrate from A to B. It's as simple as this. So it turns out if you do this, then the resulting probability measure, as they call it, is entirely consistent with the axioms we started out with. Because if you take, for example, disjoint intervals AB and CD, you require that the probability assigned to the union of AB and CD be the sum. But integral is additive, right? If you integrate over AB and then integrate over CD, if you add, it's like integrating over the two intervals, or supposing you say A to B and B to C, for example. It's the same as integrating from A to C, is it not? So the additivity property is automatically satisfied for disjoint intervals. Right? And P of omega is what? Obviously 1. Of course, when for P of omega we only, I mean if you say minus infinity, you're not going to write all these other things, you just write the open interval. That by definition we have taken it to be 1. And no matter how small we make this is never going to be negative, because f is constrained to be what? Non-negative. So this integral can never be negative for all AB. Note that this is only, right, I mean this is the most popular way of assigning problem, and can we cover all of these? Yes, we can. We have covered open intervals, we have covered closed intervals. It turns out that if you look at individual points, you will get what probability? 0. Then limit b tending to a of P of, let's say, AB is 0. So individual points, right, have, I mean this is roughly speaking, I don't think I can, I mean you would have to put some more mathematical rigor into this, but I am just roughly saying it, assuming that A is fixed and you can move B towards A or something, right, that is what I mean by this, right. If you make the B go and fall on top of A, you find by this, right, construction you will only get 0. So individual points, right, have 0 probability, but does that mean individual points cannot occur? No, it just says that the probable only intervals have finite probabilities, but if you look at this particular point in an interval and ask for the probability of observing that point measured to infinite precision by this kind of a construction, such a point will have 0 probability. And not only this, a countable union of such points AI is also, probability assigned to such a set is also 0. In other words, this the countable union of individual points again has 0 probability. That is, the probability of observing A1 or A2 or A3 is also 0. Only intervals, that Riemann integration assigns a positive quantity, positive measure only to intervals, right. So, and obviously there is no shortage of such functions, right. We will see several examples, right, and all of you have studied them in various maths courses earlier, right. So there is no shortage of such functions. So the question is again, the maths does not tell you which function to use in a particular situation, right. It is up to you, you have to figure out what is a function best suited for the problem at hand. If you have a spinning pointer which can come to rest at any point on the circle, right, you might want to assign what is called a uniform probability measure in a continuous sense, right, not discrete sense. If I take 0 to 2 pi in radians, right, omega for a spinning pointer, and note that I am leaving out 2 pi. So then I will say f of x is 1 by 2 pi. So e.g. this is just an example, right. This is one possibility. What does this mean? It says that no interval is going to be favored over any other interval of the same width. Getting between 0 and pi by 4, the probability of a pointer coming to rest in that interval 0 to pi by 4 is exactly the same as any other interval of width pi by 4. The interval is, the probability is dependent only on the width of the interval, not on the location. In fact, this is what is called a uniform distribution in the continuous space, right, and typically you start with 0 1 rather than 0 2 pi, but since we started with spinning pointers, I have to and angles I am taking it as 0 to pi. So this 1 by 2 pi is a normalization. This 2 pi will go away if you make the upper limit equal to 1. That is the all important uniform 0 1 distribution. We were taking this, we are going to take the sigma algebra F to be the Borel sometimes just called Borel field, right, and you can of course narrow it down to this portion of the real line that you are interested in. You do not have to look at all the Borel subsets of the real line, right. For example, in this pointer case we are only looking at omega equal to 0 to 2 pi. It does not really make sense to consider sets like minus 10 to minus 5 and so on and so forth, right. So so this collection of sets, right, are going to be assigned probabilities. How we are going to assign probabilities? One way of assigning probability is the and members of this Borel field are called Borel sets, right. Let me write this thing out in full. Probability density function with emphasis on density. So again, what do I mean by Borel sets? These are elements or members of the Borel sigma field itself, right. So what are the properties of this probability density function? We are going to call it PDF from now on. We will use this lowercase small letters PDF, right. The PDF, so the requirements in the PDF, let us say, and emphasize this is just one way of doing this, that is, it should be first of all integrable, or let me even be more start from even a more basic viewpoint. It is basically the domain of this F. Minimally it must map, right, it must be defined for all points in omega, right, and this R plus is sometimes is a notation used for what, non-negative real numbers, right. So that this non-negativity is very, very important, right. If it takes any negative values, it cannot be a PDF. So at a minimum it should be defined for all points in omega, but most people consider an extended definition by looking at the whole real line. So let me say that is just a convenience, right. So extend domain of F to all of R. How do you do this? By setting f of x equal to 0 for what? X not in omega. So this is typically done just to keep our thinking straight, right. We have some function which takes non-negative values only or positive values only in the set omega, which is the portion of the real line that we encountered in an experiment. Such is a pointer which spins between 0 and 2 pi, or any other limited portion of the real line for any particular experiment that we care to consider, right. But this typically the way in which these probability density functions are defined is to define them to be 0 outside omega as well, so that there is no confusion. Basically this is just to avoid confusion, right. So therefore if you integrate 0 functions in over any interval, you get 0. So the idea is to say that if you look at intervals outside omega, even though they are not strictly speaking part of this Borel sigma field itself, you can say that they are basically null events, right? For the case of a pointer, any interval which is in the negative portion of the real line is a null event, it will never happen. So it has 0 probability, and that's consistent with this. Okay, so okay, so having taken care of this, so then we also want some smoothness constraint on f. We don't want it to arbitrarily jump around. So how do we impose a smoothness constraint on f? Okay, before that let me say, so smoothness constraint is necessary so that it becomes integrable. This I did not say yesterday, I will put it here even before the integrable condition. So we will want a countable, at maximum we want, let us say, okay, not even countable, but I haven't written it, I'll keep that, countable number of discontinuities. We don't want to have the thing jumping all over the place. I mean, maybe I should have started with f here. Anyway, f has, okay, I'll just say in f. So this function does not arbitrarily jump around, like for example taking one value for real rational numbers and a different value for irrational numbers. If you think of such type of functions, they mathematically it might be okay to define something, but is it integrable? So this has to do with the integrability constraint. So f must be integrable, and not only, I mean, integrable in the Riemann sense that we have been studying all along. So there are different methods, definitions of integration, and some of you may have seen it, right? But we are going to only stick with the standard Riemann integration that we've encountered all these years, right? Ever since we started studying integration in high school or whatever. So this integral over omega f of x dx must be equal to 1. It must be non-negative and is integrable. Integral over the omega must be 1. This is just a normalizing condition, right? Even if this integral is finite, that's sufficient for us, because we can always normalize by the finite value of the integral to get unity, right? So basically we can consider any f which is non-negative and integrable and having a finite integral. So this I know yesterday I may have written minus infinity to infinity, but fundamentally you want its integral over the set omega to be 1. Of course this automatically will mean the integral over minus infinity to infinity is also 1 using the extended definition, right? Because we have said that we can, if necessary, we can extend it to cover the entire real line. So therefore most textbooks will only give this, but remember what they really mean is this. What they really want is this. In the case of the spinning pointer, you want the if you don't like the uniform. So yesterday's case was the pointer. The uniform probability distribution is what? Just because 2 pi is the same as 0, I am just saying that the domain is closed on 0 and open in 2 pi, but that is just a technicality, I just let it. So even if you did not want like this particular distribution, if you wanted a different distribution, you can go ahead, right? All you need is any non-negative function f which integrates to 1 nominally or any finite value over the interval 0 to 2 pi, that will suffice, right? And obviously there is an infinite number of such functions, right? And so there is no okay. So as in the discrete case, in the continuous case also, we do not, the theory does not care about the physical meaning of, or the whether there is actually gives you useful probabilities or not is not something the theory worries about. The theory only cares about the mathematical consistency of the definitions, that is it, right. Okay. So this is just the example. The most important point is that the probability, as I said yesterday, of any interval a b is the integral from a to b of f of x dx. Now here you can ask, where are these points a b? Typically both a and b will be the interval a b will be in omega, or this is a closed open interval just for the sake of completeness. Suppose typically this will be in okay, this will be in that Borel, okay, it does not matter, this interval in, I will just say, I will not say element in. So, but it turns out that using again the extended definition, you can take any 2 points a b on the real line. Definitely this is true, this is true for all a b element of R using extension, right. And the point is that because you get a null event, right, you do not have to say that it is explicitly 0 or something. You can live with this integral of a 0 function and you do not have to keep making special cases, right. But the non-zero probabilities are obviously going to come only here. They cannot come from the general extended domain, extended definition of f, right. And more importantly, if I have a union of disjoint sets, what will this be? This will be the sum from a to b plus the sum from c to d. That is the additivity property, which is automatically satisfied because integrals add, right. So if they are disjoint, so this is the additivity property, right. So all these things go to show that defining this, the probabilities by this, is perfectly consistent with the axioms and so on and so forth. Okay. What are more properties of this f? Remember, this f of x is not a probability for any value of x. Union, right, AB union CD. Okay, let me go back up here and start. The values of f of x themselves are not probabilities. Am I going okay so far? Any questions? Oh. This is a very constant source of confusion among students. That is, it is only f of x is only a probability density. You have to integrate f of x to give you a probability. This is where the PDF differs fundamentally from a PMF. A PMF is a collection of probabilities, but the PDF is not a probability. Only thing you know is that this f of x is non-negative, but it turns out it can be infinitely large also in some cases, as we will see. There is no constraint on, no upper limit on the value of any f of x. F of x, when I say f of x, I am talking of the particular value of f at some point x, right. Please distinguish between a function f and the values f of x. So f of x is not a probability. This is understood by everybody, right. You can get any arbitrarily large positive values here, need not be bound to between 0 and 1, because you are integrating and examples will follow, right. What is the probability of this? If I take some interval x0 to x0 plus dx for some small x, so small dx, what is this going to be? This is by our usual calculus approximation, first order approximation, Taylor series, whatever you want to call it, is what? What is this for a small interval x0 to x0 plus dx? What What is this? What happens in that if I put this in terms of this integral? Can I simplify this integral when a is x naught and b is x naught plus delta x? It will be when I said this dx is not the same as, I mean maybe I should use some other dx here, but it does not matter, just so this is basically typically dx is positive in such, right. So when dx is much smaller than 1, which means it is a small increment, this is the connection between f and probability, that is the probability of any small interval, and we already said this yesterday, p of this x naught for any x naught in omega or wherever, this is, I said 0, but you can think of it as being vanishingly small. So if I make this dx go to 0, yes, the right side RHS does in fact go to 0, but that is not to say that this x naught is a null event. It is not a null event, right. So here we have an example of getting 0 probabilities for something which is not a null event, remember, right, because when you do the experiment you do get some real value, some x naught, but a priori the probability of getting exactly that x naught is vanishingly small a priori, but it turns out we can actually condition on that particular observation x naught, but that comes later. Even though it has vanishingly small probability, we can. So essentially whenever we think of x naught, we are actually thinking of some small interval like this, which is also consistent with engineering because it is allowing for some, what shall we say, imprecision in specifying the value of x naught, right. Or if you do not like x naught to be at one end, you can put it in the middle and say x naught minus dx to x naught plus dx or whatever, or you can do any of that stuff, but essentially this kind of thing is just reflecting our imprecision in specifying or measuring exactly a real number, which we cannot in any way do in practice. So this and why do we need, and I guess it is clear that we do need some smoothness constraint, right. We want an integrable function essentially. We do not want some crazy function which, right, mathematicians are right fond of constructing, and then we do not want to pull our hair out saying how the hell do I integrate this, right. So that is why I am saying right up front in all our probability models of PDFs, this f will be integrable. It will have, if at all it has jumps or discontinuities, they will be finite in number, countable, not even countably infinite, they will be finite. You can count them on the fingers of even just one hand, not even two hands, right. So integration is not a problem essentially. So I think, okay, so as of now, I mean let me not anyway we are going to see a lot more of this probably PDF later on. So we will move on to a different way of specifying, of assigning probabilities, right. Maybe I should have put delta x here to differentiate this dx from this dx, it does not matter, right. I do not think it is a major confusion, right. You can write, you can use something else out here, you can put dy if you want, or delta, anything. Okay. So maybe I should also specify this is assuming that dx is positive, right. I do not want somebody to get up and say what if it is, right, are you looking at very large negative numbers? No, I am not.